In this video, we are going to find the Mobius transformation that sends the points 0, 1, infinity to -1, 0, 1, respectively. So here we want to map 0 to -1, 1 to 1 to 0, and infinity to 1. Okay, and this is t. Instead of using the implicit formula, we are going to just go with the direct deduction here. Okay, we are going to deduce directly the formula. This usually works best in the examples. So here, remember, the best way to start is always looking at what goes to 0. That one goes first. And the way we do it, we are going to be looking at the quotient, all right? So here we want to make sure that when we plug in 1, we get 0, all right? So z minus 1 is our candidate. Okay. Now, as we saw, infinity is usually the second easiest choice. Okay, in this case, if we want to get 1 when we plug in infinity, we need a coefficient of 1 next to z, right? So this is infinity, infinity, we get 1. The constants here are irrelevant. Okay, we will always get 1. And now we just need to make one last adjustment and make sure that the third point gets mapped where it should. Oops. So that's going to be the third point. Okay, this is the second. And this goes in green. And here we put the orange. I like this better color coded so that we can visually identify what is going where. Okay, so what do we need to put there? What constant do we need here so that we satisfy this condition also? All right, when I plug in z equals 0, clearly I need some constant, because if I divide by 0, then I would end up at infinity here, and that's not the case. What is the constant? So I want to get -1. So getting 1 here will do the trick. So I need to put the +1. In this case, let's check one more time. 1 goes to 0. All right, this goes to 0. This is 1 + 1, 2. 0 divided by 2 is 0. Nice. Infinity goes to 1. All right, also nice. And 0 goes to -1. Also satisfied. So this is our mapping. This is the transformation. There are other ways we could go about this. We could just apply the implicit form right away. We could say W2 minus, what happened there? W2 minus W3 divided by W2 minus W1, W minus W1, W minus W3 equals Z minus Z2 minus Z3, Z2 minus Z1, Z minus Z1, Z minus Z3. Okay, and here we just need to plug in what is what. But it is a bit of a pain, right? So these are my W's, these are my Z's. Okay, so these are Z's, these are W's. All right, so let's do it. So we have W2, which is 0 minus 1 divided by 0 plus 1, because it's minus 1, times W minus W1, W minus W3 equals, and here the Z's. So this is 1 minus infinity. Don't get alarmed. Z2 is 1 minus 0. And here we have Z minus Z1, which is 0. Z minus Z3, which is infinity. Okay. So this is going to be 1. All right. Not quite 1, right? these two together make one, but we still have the other two. All right, so this is not quite correct. What I get here is z. And from here, we just notice, right? There's a minus sign here. We have w plus 1 divided by w minus 1 equals minus z. That means the minus, remember, comes from here. All right. So that means w plus 1 equals minus zw plus z. So that means sending all the w's to the left, we have 1 plus z w, right? Equal z minus 1. And then w equals z minus 1 divided by z plus 1, which is what we got before. Perfect. You see, this is another way we can get it. Notice that in this example, we haven't quite followed the algorithm that we said, because strictly speaking, the algorithm would be sending these points to 0, 1, infinity. We just went straight for it because this was these numbers were very easy to identify, okay? The mapping is very easy to identify. If the numbers are more complicated, we just do it in 2 stages, as we saw in the proof. Let me just comment on what is happening geometrically here. Okay, so we have 2 copies of the complex plane. Okay. And what do we have? We have the 3 points. We have 0. We have 1. And we have infinity. Okay, infinity, we can't really plot it, of course. And then they end up in -1. Then we have 0. And then we have 1. Okay. What is happening here is that this Mobius mapping T, this Mobius transform T, is sending the circle, okay, that is the real line with the point of infinity. That's a circle in the Riemann sphere, right? If you look at the sphere, okay, we would be talking about this circle over here, all right? Because when it extends into the real line, okay? Anyway, then the image, this is another circle in the Riemann sphere that passes through t of 0 equal -1, t of 1 equal 0, t of infinity equal 1. Okay. So let's see what part gets mapped where. So notice here, t of 0 is -1. Okay, so this one gets sent here. T of 1 is 0. So this one goes here, this one goes here. But we are going to see this segment is going to end up here. And we are traveling this way. Okay. Now, t of 1 is 0. Okay, and we have that t of infinity ends up in 1. So this segment here is going to end up here. So we have this whole segment that ends up here. Okay, and still we're traveling this way because t of 1 is 0, and then t of infinity is 1. Now, the funny part, we have t of t of infinity, right, is going to be 1. So we are going to get this part here is going to get mapped here, and this looks like it's two pieces. Watch out, because it's actually one piece. This is, you see, coming from infinity to zero, this is an arc in the Riemann sphere. Okay, we are talking about this part of the arc. Let me just go ahead and actually draw how these things look in the Riemann sphere. I think that will be much more helpful. So let's say we have here our Riemann sphere, okay? And remember, this is the point of infinity. This is -1. This is 1, okay? And here, this point is the point that gets mapped to 0, okay? Now remember, the complex plane is right here. So we map using the stereographic projection. Let's make a copy here. So let's start with the part that goes here from 1 to infinity. 1 to infinity means that we are going in this direction. Okay, and that gets mapped from 0 to 1. So that gets mapped here. Okay, now the part that goes from from infinity to 0, right? That's this part, this arc, all right? That gets mapped to the part that goes from 1 to -1, but going through infinity. So it gets mapped here. All right, you see why it looks like it has two pieces? It looks like two pieces because the point of infinity is so far away. Okay, but in the Riemann sphere, it has only one piece. And then we have the last part, the orange one, that goes from 0 to 1. Okay, from 0 to 1, that gets mapped to -1 to 0. Okay, so actually this makes a lot more sense. What happened in the Riemann sphere, actually? The Riemann sphere just rotated around, the points rotated around, and that's it. Now, geometrically, it may make more sense to you.